What if some of the biggest turning points in human history began with a simple mistake? What if entire civilizations shifted direction because a few brilliant minds were certain they were right, only to discover they were completely wrong? And what if the science we trust today carries the same potential for failure? For centuries, the world has moved forward because of discovery, but it has also stumbled because of misplaced confidence. A single error in a laboratory has triggered decades of confusion. An innocent assumption has shaped national policies. A flawed calculation has rewritten textbooks before anyone even noticed. There are moments when science didn't just make a mistake, collapsed under its own certainty. And every time it happened, humanity paid a price. One of the most striking examples comes from the early 20th century, when respected researchers believed they had discovered a new element that could revolutionize medicine. The claim spread like wildfire, endorsed by professionals who never questioned the data behind it. Within a few years, the supposed discovery was revealed to be nothing more than an illusion created by contaminated equipment. Yet by then, the world had already embraced it as fact. Another historic failure emerged from the belief that continents were fixed and immovable. This assumption shaped geography, geology, and education for generations. Anyone who suggested otherwise was dismissed, even mocked. It took overwhelming evidence, new technologies, and relentless persistence to prove that continents drift like slow-moving rafts on a molten sea beneath our feet. These stories matter because they ask a simple but unsettling question. If the brightest minds of the past could fall for illusions, what illusions might we be living with right now? The deeper we look into the history of scientific errors, the more we notice a pattern. Mistakes rarely come from ignorance. They come from confidence, authority, and the comfort of believing the world works exactly as we expect. This video explores how some of the most influential ideas in history turned out to be wrong. It examines the mechanisms that allowed those errors to grow, the evidence that eventually shattered them, and the unresolved questions they leave behind. The goal is not to undermine science. It is to understand how fragile truth can become when humans stop questioning it. And maybe that is the real warning behind these failures. Not that people made mistakes, but that almost no one thought they could. Imagine standing in a room lit by an old, flickering bulb. The light seems steady at first, but every few seconds it dips just enough to make you doubt your own eyes. Scientific certainty often works the same way. It looks stable until a tiny, almost invisible flaw reveals how fragile the entire structure really is. That fragile structure begins with assumptions. In everyday life, assumptions help us move quickly. If a chair looks sturdy, we sit without checking every joint. Science does something similar, but on a much larger scale. It builds theories by assuming that measurements are clean, instruments are reliable, and observations are free of bias. When any one of those assumptions cracks, the whole chair collapses. In scientific terms, this crack is called systematic error. It is a hidden, repeating flaw that pushes every result in the same wrong direction. Unlike random noise, which scatters data around the truth, systematic error quietly bends reality itself. Historians of science often trace major failures back to these invisible tilts in the data. A classic example is the early search for new elements. Researchers believed they had discovered substances with strange properties, but many of those discoveries later turned out to be contaminated samples or miscalibrated instruments. The mechanism behind these failures is simple but devastating. A misaligned tool produces consistent but false signals, and human confidence fills in the rest. This raises a natural question. How often do hidden flaws shape what we believe today? Evidence of historical scientific mistakes reveals several clear patterns. One pattern is the role of confirmation bias, the tendency to see what we expect. In the 19th century, astronomers reported a non-existent planet called Vulcan, convinced it must be hiding near the sun to explain irregularities in Mercury's orbit. Their observations were sincere, but shaped by an assumption that Newton's laws had to be flawless. Another pattern is technological limitation. Before modern imaging, early biologists misidentified cellular structures, sometimes mistaking artifacts for living components. The observations were real. The interpretation was not. These moments remind us that evidence is only as strong as the tools used to collect it. A third pattern comes from social pressure. Once an idea gains acceptance, challenging it becomes risky. Continental drift was dismissed for decades, not because the idea was weak, but because the scientific community feared undermining an entire worldview built on fixed geography. The evidence existed, the willingness to take it seriously did not. These observations set the stage for deeper questions. What if alternative explanations existed all along? What if the failures were not just wrong answers but wrong frameworks? The null hypothesis, the idea that we should assume no effect, no discovery, no new phenomenon until evidence becomes overwhelming, exists for this reason. It forces science to argue with itself before making claims. In the case of continental drift, the null hypothesis favored stability, and early data seemed too vague to overturn it. Only when magnetic patterns in seafloor rocks aligned perfectly with drift models did the balance shift. Alternative models often emerge quietly, like faint signals beneath static. They gain strength when they explain anomalies that established theories cannot. Yet even then, they face resistance. Vulcan eventually disappeared not because someone proved it wasn't real, but because Einstein's relativity provided a better explanation for Mercury's strange orbit. The old model collapsed because a new one finally matched reality more closely. Still, major gaps remain. Even today, entire fields rely on models that work well in practice but remain incomplete in principle. Climate feedback loops, dark matter behavior, and the origins of complex diseases all contain layers of uncertainty. Predictions are strong but far from perfect. The limits of instruments, the complexity of nature, and the biases built into human thinking continue to leave blind spots. These blind spots are not signs of weakness. They are reminders that knowledge is a moving target. Every answer opens a new set of questions, and every model works only until something unexpected breaks it. The failures that shaped scientific history were not random accidents. They were the natural outcome of human beings trying to understand a world far more complex than they imagined. The early questions of this story asked why brilliant minds made mistakes that now seem obvious, and the answer begins with the same patterns visible across centuries of discovery. One of those patterns is the quiet power of assumptions. The belief that an experiment is clean, a theory is complete, or a measurement is precise has led researchers into some of the most famous dead ends in history. In the case of the phantom element once believed to cure illnesses, the failure emerged not from ambition but from trust in equipment that was fundamentally flawed. When tools produce consistent but misleading signals, confidence grows faster than doubt, and certainty becomes a trap. Another major pattern is the influence of technological limits. Astronomers who believed in the existence of the planet Vulcan were not careless. They were using the best instruments available at the time, and those instruments simply could not capture the gravitational subtleties needed to reveal the real cause of Mercury's strange orbit. The hook question of how science can fail so completely finds part of its answer here. Tools define the boundaries of knowledge, and when those tools improve, entire worldviews can shift overnight. A third pattern lies in social momentum. The scientific community, like any human group, relies on shared beliefs to organize knowledge. When the idea of fixed continents dominated classrooms, journals, and institutions, it created a kind of intellectual gravity. Even strong evidence struggled to escape it. The story of continental drift shows how the weight of group consensus can delay the acceptance of a correct idea for decades. These mechanisms explain why the questions at the start of this video were not exaggerated. Science failed in these moments because confidence outpaced evidence, because instruments could not illuminate what they needed to, and because communities resisted ideas that threatened long-standing assumptions. So how should these failures be understood? They reveal that scientific progress is not a smooth line but a series of corrections. Every major mistake contained the seeds of a breakthrough. The contaminated samples that created the illusion of a new element eventually led to stricter laboratory standards. The absence of Vulcan forced physicists to rethink gravity itself and paved the way for general relativity. The rejection of continental drift inspired a new generation of geologists to challenge established norms, ultimately building the foundation of modern plate tectonics. The hook questions also asked whether similar illusions might exist today. The answer, based on history, is yes. Complex fields like climate science, genetics, and cosmology contain unanswered questions where assumptions still influence interpretation. These are not signs that the fields are broken. They are reminders that certainty should always be temporary. Scientific failure does not mean collapse. It means recalibration. It means letting reality correct the story we write about it. And every example from history shows that progress was strongest not when people were right, but when they recognized they might be wrong. Scientific mistakes are more than historical curiosities. They show how fragile certainty can be and how quickly our understanding shifts when evidence demands it. Every failure becomes a reminder that knowledge grows through correction, not perfection. These moments reveal a simple truth. Science moves forward by admitting what it does not yet know. Assumptions break, models change, and the world becomes clearer each time we revise our own beliefs. If this perspective offered something meaningful, feel free to subscribe to the channel and share your thoughts in the comments.